Hello, everyone, and welcome to episode 72 of the Stanford MLSys seminar series. Of course, this quarter we are also joined with the lovely Advances in Foundation Models class at Stanford CS324. Today I have with me Ivanica and Michael from the class, so go ahead and wave, say hi. And our guest today is Colin Raffel. So a little bit about Colin. He's an assistant professor at UNC Chapel Hill. He's a faculty researcher at Hugging Face. He says that his work aims to make it easy to get computers to do new things. He's done some very exciting work in machine learning, and today he's going to talk to us a little bit about building machine learning models like open source software. So we're very excited to hear from him. Go ahead, Colin, take it away.
Thanks a lot, and thanks for having me. So yeah, today I'm going to be talking about a major research direction in my group that, as Dan said, it aims to make it possible to develop machine learning models like open source software, or in other words, enable collaborative, communal, and continual machine learning. So I'll go ahead and get started. So, a decade ago, when neural networks really started to become a powerful tool for machine learning again, the standard way to use them or train them is kind of diagrammed on the screen here. So we would take a model, maybe randomly initialize its parameters, take usually a large labeled data set, and then train the model on that particular data set, and then use it to process examples from the same data distribution. And so here I'm showing some examples from computer vision for various tasks we might want to perform, like mushroom classification or segmentation or chest X-ray diagnosis and so on. And each of these models might have some commonality in terms of the model architecture and how they're trained, but there's no real shared capabilities or knowledge across these models. They're all trained independently on separate data sets. Of course, that's not really how we do things now. A much more common paradigm is to first take a model and train it on a large kind of general purpose data set. And this step, which we call pre-training, has proven to be a really, really valuable first step before we do subsequent training on the actual data sets and tasks that we care about. So here I'm showing an example where we pre-train the model on the ImageNet data set, which is a very diverse, large-scale image classification data set. That pre-training step has been repeatedly demonstrated to be a very beneficial step before subsequent fine-tuning on these downstream tasks shown on the right. That often makes fine-tuning converge to a better solution more quickly with less labeled data. So a lot of the time it's really a no-brainer. And this kind of adaptation isn't always done via fine-tuning. There's lots of ways of adapting a pre-trained model to a downstream task. Increasingly, when talking about language models, we can often adapt them to downstream tasks by, for example, providing natural language descriptions to the model. But the key point that I want to make here is that this pre-trained model is really a very valuable artifact. It's a shared artifact that's reused over and over again for many, many different purposes and by many different people, and kind of becomes a cornerstone of a lot of applications of machine learning. Now, one of the really nice things about this recipe, this transfer learning recipe that I just talked about, is that because the pre-training stage often can make use of a very large scale data set that is either unlabeled or involves self-supervised learning or even weakly supervised learning, it's often possible to really scale up the size of the pre-trained data set. And when we scale up the size of the pre-trained data set, we also have the opportunity to scale up the size of the model that we're pre-training. And as a result, we've seen a lot of plots like I'm showing on the screen here, where on the x-axis, we have some measure of compute. On the left, model parameters, and on the right, the pre-training compute. And on the y-axis, we see some measure of performance. On the left, this is accuracy over a collection of natural language processing tasks. And on the right, this is an error rate, so lower is better on ImageNet. And again, one of the really fruitful things about the transfer learning recipe, this pre-training step, is that we can often scale up the size of the pre-training data and the pre-training model and just see more and more and more improvements on the tasks that we actually care about. And this is really nice because the kind of what we need to do in order to get improved performance stops being a research problem and starts being instead more of like an engineering problem of how do we actually train these large scale models and manage these large data sets. And so this is really nice, but it's also not so nice in the sense that increased scale increases costs. So for example, looking at the plot on the left, these are a bunch of recent or relatively recent large language models. We actually can think about what would be the financial cost of training one of these models today, or at least at the time it was developed. So GPT-3, which is one of the large language models that's shown on the plot on the left, would have cost about $5 million to train in 2020. Gopher and Chinchilla, about $7.5 million in 2021. And the PaLM model that was announced by Google in 2022 would have cost about $27 million at the time. So this is a pretty large amount of money. It's out of my budget as an academic. And the situation is a little less dire in computer vision. Kind of the most expensive point on the plot on the right would have cost about $750,000 to train, but still a really huge amount of money. So this really beneficial scaling property it has produced major benefits, but has also really made the development of pre-trained models out of reach of many people. And that's one of the things that I'm going to be talking about today. As a kind of maybe a consequence of the increasing costs of these models, we have also increasingly seen pre-trained models that are not released to the public. I think for a long time, many of the most powerful pre-trained models were released publicly, but in the last few years, it's increasingly common for resource-rich institutions to train models and then keep them private either for their own uses or to put them behind a service like an API for people to pay for access to. And while this can maybe provide a nice business model for these companies, it makes it so that there is less kind of open sharing of information and research advances among the community at large. And for those models that are released, as I mentioned earlier, they do see a staggering amount of reuse. So here I'm looking at the top, in this case, 7 models from the Hugging Face Model Hub, which is just a big repository of trained models, basically. And if you look at the most popular pre-trained models in the Hugging Face Model Hub, first of all, they're reused a lot. And these download numbers, if you can see them, only account for the downloads in the last month. So in this case, it's saying BERT base, which is a pre-trained language model, was downloaded about 30 million times in the last month when the screenshot was taken, which is really a staggeringly large amount. And the same is true for many of these models here. But what I want to highlight is, first of all, that all of these models were actually created by relatively resource-rich institutions, because again, the cost to build these models is quite high. But also, importantly, these models were developed by some institution, released, and since then have not been changed or updated or improved in any way. BERT was released in 2018. It's now 2023. So almost 5 years later, we're still using exactly the same pre-trained model. It's still the most widely used pre-trained model on the Hugging Face Model Hub. And it remains exactly the same, even though the field has moved on and advanced and produced significantly better models. We're still using the same model. It hasn't been improved in any way. And there are reasons that we might want to update a pre-trained model. And those reasons can be either good or bad, I guess. So first to talk about maybe something that might be a problem with a pre-trained model that we might want to fix. In work that I did a few years ago with my colleagues at Google, we showed that it was actually often possible to extract training data from pre-trained models. So if you took a pre-trained model that someone had released, you could determine whether a given chunk of text in this case was used to train that particular language model. In this case, it was a GPT-2 model released by OpenAI. And just to give you a quick picture of how we figured out whether a given chunk of text was memorized or not, we basically compare the likelihood assigned by the model to the chunk of text to the likelihood assigned by another model to the same chunk of text. In this case, we're looking at the entropy of the zlib compressor on the plot on the right. And you can see that there are certain examples that GPT-2 assigns a very high likelihood or a low perplexity to, but zlib assigns a very high entropy to, indicating that it seems unlikely. And those are samples that indeed often turn out to be memorized. And in subsequent work, we showed that actually this memorization of training examples often comes from large-scale duplication in the pre-training data set. So in some sense, you can think of this undesirable behavior as being a kind of like uncovering a bug in the training details of the model. So it's not a bug in the source code, but it's an issue with the way that the training data was collected. The training data wasn't appropriately deduplicated, and as a result, we found that it was particularly easy to extract samples that were seen many times in the training data. So looking at the plot on the right, we actually saw this remarkable relationship where as the number of times a given example was duplicated in the training data set, the number of times the model generated it actually increases super linearly. Okay, so for example, if you go from a chunk of text appearing only 10 times in the training data set up to 100 times in the training data set, it actually becomes not 10 times more likely, but over 100 times more likely. And this held true across many different language models. So again, you can kind of think of this as someone releasing a pre-trained model and us uncovering a bug that we want to fix with the pre-trained model. But of course, as I mentioned, these pre-trained models are never really updated. So we're kind of stuck with these models that might have this undesirable behavior forever. You can also look at this from the opposite way. Sometimes it's beneficial for models to memorize some of the things they saw during pre-training. For example, we want them to memorize world knowledge, general purpose facts about the world. And so then we can ask kind of the opposite question, which is how many times does a language model, in this case, need to see a fact in order to answer a question about that fact after pre-training? And we found this a very similar relationship where basically the ability of a language model to answer a question about a fact is very closely correlated with the number of times that that fact appears in its training data set. And as a consequence of this, facts that appear very rarely in the pre-training data set the language model has a lot of trouble answering questions correctly about, even if they did appear, at all. And so now looking at it from the other angle, what we might say is, well, we really want our language model to be able to answer a question about this particular fact. We need to update it to provide it with that knowledge. But again, people never do this. This is not a commonly taken step in the development of pre-trained models. Of course, there are lots of other reasons to update pre-trained models. And in fact, it's not completely true that people don't update them. For example, if we look at kind of a family tree of the T5 model, which is a model that I developed with my collaborators at Google some years ago, there's actually quite a large number of models that have been derived from the T5 model. For example, kind of looking in the middle there, T5 was used as the basis of unified QA, which is a model that was trained on a kind of a wide variety of question answering data sets with a goal of being a general purpose question answering model. And then unified QA was used as the basis for Macaw, a more powerful question answering model. T5 was also used as the inspiration for models like MT5 or T5.1.1 that kind of use a similar architecture and training process, but were trained either on different data or with a slightly different architecture. And those models then were used as the basis of other models, like T5.1.1 has now been used as the basis of various instruction tune models like TK Instruct, Flan T5, and T0. And also parts of T5 have also been reused in other models. So for example, the encoder of T5, one of the layer stacks, has been used in image language models like Pali, Imagine, and Muse. And finally, T5, of course, has been fine-tuned many, many, many times, and many people have released the fine-tuned models, uploaded them to the Hugging Face Model Hub. So you can see there have been thousands of fine-tuned variants of T5. So it's not the case that there's, I should say it's certainly the case that there are reasons that we would want to update and improve a pre-trained model. It's just that we never do it. We don't have the tools to do it. It's not standard practice. So now let's stop thinking about machine learning models and think instead about open source software. And so I probably don't have to sell any of you all on this, but open source software is an incredibly valuable part of computing today. Basically every interaction you have with your computer involves open source software, probably at various points in the stack, whether it's because you're using an open source web browser to connect to a web page that is being hosted using an open source web framework on an open source web server written in open source programming language. Really, it's really all over the place. The program that you're using a lot of the time is probably compiled by an open source piece of software. And I could go on and on and on. But again, I probably don't have to sell you on this. But the key thing that I wanted to drive home here is that all of these pieces of software, by virtue of being open source, were developed by a large community of individuals working together to continually improve the software. So it's not true, for example, that a small resource-rich institution just released the Python programming language and it was left as is forever. And now everyone uses the same version of Python forever and ever and ever. That's not true at all. Of course, there have been thousands and thousands of bug fixes to Python and new features and improvements that were contributed by a giant community of collaborators. And maybe even some of you have contributed to some of these pieces of open source software. And the key point that I want to make is that this is totally different from the way that we build machine learning models, and in particular, pre-trained models. And my main motivation for this line of work and for this talk that I'm giving you now is that we should really think about what can we do to make the development of pre-trained machine learning models more like the development of open source software. And so now I'll talk about kind of some of the preliminary research steps my group has undertaken in order to realize this goal. So specifically, I'll try to answer the question of how can we enable collaborative and continual development of machine learning models. And so I'll talk about kind of various problems we need to solve and the initial steps that we've taken. So the kind of first fundamental piece of open source software development is the ability for contributors to be able to cheaply communicate changes back to a set of maintainers of a piece of software. So making the same analogy for machine learning models, if you update a machine learning model, if you improve it in some way, you need a way to communicate your changes back to the maintainers of that model. And ideally, you should be able to communicate those changes cheaply, right? You shouldn't have to communicate all of the parameters of the model back to the maintainers every time you want to change it. So how can we make it possible for contributors to a model to contribute patches, right? Small, cheaply communicable updates. And I'll talk about a little bit of our work along this direction now. Excuse me. So again, one of the main issues with the possibility, or one of the things that stands in the way of the possibility of communicating patches for machine learning models is that the way that we train neural networks today is typically via gradient descent. So at every iteration of training, we update all of the model's parameters. And if in doing so, if I make any small change to the model, if I just train it on one mini batch of data, I immediately have an entirely new set of model parameters. And so if I do any kind of training, any kind of updating at all, I'm going to need to communicate the full set of model parameters back to the maintainers, which has a pretty high communication cost, especially as these models are on the order of tens of gigabytes or more in storage space. It also would get onerous to track all of the versions of a model if we're going to keep track of tens or hundreds of thousands of changes to a model. So the key step that we undertook in this work is to basically say, well, how about instead of updating every parameter of the model at every iteration of training, what if we update a small subset of the model's parameters? Is there a way that we can pick a small subset of the model's parameters that we can update over many steps of training and still have the model retain good performance, even though we're only updating a tiny subset? And as long as this subset is small enough, the communication costs will be significantly lower. So the main question then becomes, how do we pick what the subset of parameters to update? And the way that we selected the parameters in this work are based on a quantity called the parameters Fischer information, or in particular, it's an approximation to the parameters Fischer information. And if you're not familiar with this quantity, what it basically measures is if I take a given parameter and perturb it a small amount, how much does the model's output change? So if I perturb a parameter a little bit and the model's output changes a lot, intuitively, we might think that that parameter is particularly important, right? It has a large effect on the model's outputs. And so if we measure this approximation to the Fischer information, we can choose the K parameters that have the highest Fischer information and update only those parameters for many iterations of training. And as long as K is sufficiently small, the communication costs will be dramatically reduced. So a classic way to benchmark the ability to update many fewer parameters over the course of training is in the setting that people call parameter efficient fine tuning, where you are given a pre-trained model and you want to fine tune it on a downstream task, but you want to update as few parameters as possible. And so we evaluated our approach, which we call Fishmask, the Fischer-induced sparse unchanging mask, in this parameter efficient fine-tuning method, in particular on fine-tuning the BERT model I mentioned earlier on GLUE, which is kind of a meta data set of NLP data sets that cover a kind of a decent range of natural language processing capabilities. And so in this plot on the x-axis, we're showing kind of the percentage of parameters that were updated over the course of fine-tuning. And on the y-axis, we're showing basically the validation accuracy on GLUE. And you can see, and also that I should say the dashed line corresponds to the accuracy achieved by fine-tuning the full model. And you can see that with Fishmask, we actually can update only a very small percentage of the model's parameters and still get the same accuracy as if we had trained all the parameters, maybe even as few as 0.5% of the full model's parameters. If we, instead of choosing the parameters according to those that have the k highest Fisher information values, if we just choose them randomly, then you can see we get dramatically worse performance, which suggests that using the Fishmask to choose which parameters to update is an effective way of kind of effective proxy for the parameter's importance. We can also measure the communication benefits of using Fishmask in a distributed training setting. So in distributed training, the goal is to have multiple workers who are training a shared model. And when you have workers who are training independently, they occasionally need to communicate their updates to each other. And this communication step can ultimately become pretty costly. So a major goal in distributed training is reducing the cost of this communication. So in this case, we are training a convolutional neural network on CFAR10, kind of a standard neural network architecture on a standard image classification data set. And we have two workers. And the way that we can reduce communication costs is either by delaying the updates between the workers or by basically communicating a much smaller subset of the parameters. So you can see the black line corresponds to just doing standard training, updating of all of the model's parameters. And you can see that we actually can reduce communication costs a lot by delaying the update frequency as we move to the left on the x-axis. But if we use Fishmask, we have a complementary way of reducing the communication cost by updating fewer parameters. And you can see that ultimately using the Fishmask, the dark green line, can retain the performance of full model training, but with only 10% sparsity, so updating 10% of the model's parameters. Now, if we try to only update 2% of the model's parameters, the performance is a bit worse. And if we update 10% of the model's parameters with a random subset of the parameters, the performance is a lot worse. But again, the main point here is that using the Fishmask can retain the performance of updating all of the model's parameters, but can incur a more favorable communication versus accuracy trade-off. So in more recent work, we studied other ways of updating a small subset of the model's parameters. And in this work that I'm highlighting now, instead of choosing a subset of existing parameters, we actually add a very small number of parameters to the model. And in particular, what we found was that by inserting learned vectors that are multiplied element-wise against the model's activations, which is equivalent to updating the columns, basically updating a multiplicative scale on the columns of a weight matrix, we could actually get an even better trade-off between the number of parameters updated and the accuracy. And so here, what I'm showing is where those parameters are inserted in a transformer model. If you're not familiar with the architecture, you just need to, think of this as finding some intermediate activations of the model and multiplying them element-wise by a learned vector. And because the size of the weight matrices and the rest of the parameters of the model is typically a lot larger than the hidden dimensions of these activations that we're multiplying against, we are inserting a very small number of parameters when we introduce these learned vectors. So if we again measure the performance of this method that we call IA3 in a parameter efficient fine-tuning setting, we can again measure the percentage of the parameters updated versus the accuracy. And I should say this is no longer BERT on GLUE, it's a different model on a different set of data sets, but the setting is very similar. And we again show the performance of updating all of the model's parameters with the dashed black line. We actually found that IA3 could outperform updating all of the model's parameters and also outperformed every other parameter efficient fine-tuning method we considered, ultimately only updating about 0.01% of the model's parameters. So really a very tiny subset of the model's parameters were sufficient and actually beneficial in this parameter efficient fine-tuning setting. And so to give you a sense of this, these experiments were run on a model with about 3 billion parameters that would require about 10 gigabytes of storage to store. Using IA3 on this model only requires a few megabytes of storage, a little bit more than the amount of storage required for amount of storage available on a floppy disk, but not too far off. Okay, so first we talked about patches, some of our preliminary work of making it possible to communicate a very, very small amount of information to change a model meaningfully. Now let's talk about how another major important step in collaborative open source software development, which is the ability to merge improvements. So if I have a shared artifact and you propose some updates or improvements to it, and someone else proposes some updates and some improvements to it, we need a way to take those updates and combine them in a way that retain the benefits of each of your respective updates. And so in open source software development, that's called a merge. In machine learning, we don't really have an analogous operation for merging. So now I'm going to talk about kind of a way to make merging possible. So the goal again here will be, if we have a shared model and individual contributors do different training on the model, how can we combine their training, their updates, in a way that retains the benefits from both of their independent trainings? So to kind of give you a picture of what this might look like, here are kind of some diagrams of the way people typically use pre-trained models today. So we might take a pre-trained model shown in blue, updated on fine-tuned on a downstream task that gives us a new model shown in green. Sometimes people do somewhat more sophisticated things, like they take a pre-trained model, they do an initial stage of fine-tuning on what we might call a donor task, and then they do some final fine-tuning on what we would call, the downstream task, the target task. And this is really all we can do. We can do these kind of linear graphs of model updating. But what merging enables is stuff like this. So for example, looking in the top middle there, we could take a pre-trained model. It could be independently trained on a donor task and a downstream or fine-tuned task. And now the goal will be to combine these two models to simulate intermediate task training. In other words, to retain the benefits of these individual training runs to boost performance on the fine-tuned task. We can also do things that look like ensembling, shown on the left there. We take a pre-trained model, we fine-tune it many times on the same data set, with different random seeds. And then we can imagine merging all those models together to get a single model that hopefully works as well or better as all of the individual fine-tuned models. We can also consider very unusual things like what's shown on the right there, where we take a pre-trained model, we do intermediate task training on the top, but then we also do donor task fine-tuning on the bottom. And now our goal is to kind of do this like doubly intermediate task training setup that would just be completely impossible with sequential fine-tuning. So how are we going to do this? Well, in this paper that I'm discussing now, we formulate this problem via the following optimization problem, okay? And the goal here, the high-level goal, is that we're going to try to find the set of parameters that maximizes a sum of the individual model's log posterior distributions. So the posterior distribution gives us a probability of a given parameter setting given the data set that is used to train the model. I should just briefly mention that the lambda I hyperparameters shown here can be set by hand to basically up or down weight the importance of some particular model based on heuristics. And so the trouble with solving this optimization problem is that we, in practice, when we train neural networks with gradient descent with maximum likelihood, the way that we always do, we never have access to the log posterior or the posterior distribution for that particular model. So a very common approximation to make or a very simple approximation, I should say, is to approximate the posterior as a Gaussian distribution, whose mean is on the parameter values found via standard maximum likelihood training. And in this case, a very simple assumption to make is that the covariance matrix is an identity matrix. And so if we make this assumption, basically assume that the model's posterior distribution is centered around the found parameters with identity covariance, then this optimization problem I've written at the top has a closed form solution shown on the bottom. Basically, we just take a weighted average of the models, each individual model's parameters, where the weighting is set according to the lambda I hyperparameters that I mentioned earlier. And because we're approximating the model's posterior distribution as an isotropic Gaussian, we call this isotropic merging, okay? But we can actually go one step further. So if we replace the identity covariance matrix with the inverse of the Fischer, this is the same Fischer the Fischer matrix that I talked about earlier, and I should mention again, this is an approximation to the Fischer. We can get hopefully a better approximation to the posterior distribution because we're doing what's called the Laplace approximation. It turns out that the precision matrix at a mode of the posterior distribution is very well approximated by the Fischer. So if we can get a good approximation of the Fischer, then hopefully we can get a decent approximation of the posterior distribution. So if we make the Laplace approximation, then we again end up with a weighted average, but now there's an additional weighting that's a per parameter weighting that is in accordance with the parameters Fischer information. So another way to think of this is basically how important is this parameter according to its Fischer information. And I'm going to use that importance to upweight or downweight different parameters from individual models. And so we call this merging method Fischer merging. And our main question now is using Fischer merging more effective than using isotropic merging? So to answer that question, I'll present a couple of experiments. The first is in the setting that was introduced in a paper called a robust fine-tuning of zero-shot models. And the idea in this paper was we're going to take a pre-trained model, we're going to fine-tune it on a downstream data set. In this case, they call it an OOD, an out-of-distribution data set. And then we're going to merge together the two models by averaging their parameter values. And in doing so, the goal is to get a better trade-off between the performance on the pre-training task and the performance on the OOD task, the fine-tuning task. So if we sweep lambda, we can kind of trade off those two accuracies. And what we're going to hope to see, or what we do see in practice in the plot on the right, is that by using Fischer merging, you get a more favorable trade-off between isotropic merging, between the pre-training accuracy, the ImageNet accuracy, and the OOD, the fine-tuning accuracy. Basically, the circles are kind of to the right and above the x's. Okay, so in this case, Fischer merging gives us a nice boost over standard parameter averaging. So now let's focus on that kind of unusual merging pattern I described earlier in a very specific setting. So we're going to take BERT again. We're going to fine tune it on MNLI, which is a natural language inference, kind of a standard NLP data set, and then fine tune it again on RTE, another natural language inference data set. And then we're going to separately take BERT and fine tune it on a donor task. So these are the tasks that are shown along the x-axis on the plot on the right. And our goal here is going to be to merge together the donor model on the bottom and the RTE model on the top to maximize the accuracy we can get on RTE itself. So the dashed line in this plot just shows the accuracy of the RTE model itself, and the bars show the accuracy that you get from performing this merging. And you can see that for actually all of the donor tasks that we considered, we get a significant boost in accuracy when when merging in a donor model. And again, this kind of training pattern would be basically impossible with standard training, because by the time if you were to take the RTE model, if you're going to take the MNLI model and then train on the donor task and then on the RTE task, we suffer from what's called catastrophic forgetting and continual learning, and we no longer get the benefits from training on MNLI. And so in practice, the performance is actually sometimes even worse than the dashed line here. So this really shows that the ability to merge models in this way kind of opens up new paths for transferring capabilities across models. And in more recent work, we showed a new application of merging that we call cold fusion for collaborative descent. And in cold fusion, the idea is that if we have a shared pre-trained model, which we call a base model in this diagram, and then we take that model and a bunch of people fine-tune the model on all kinds of different data sets. And then we take the fine-tuned models and we merge them together. We average the values of their parameter values. And then we use that as the new base model, as the new pre-trained model for subsequent stages of distributed fine-tuning and averaging. Then what we hope to see and what we do see in practice is that the base model just gets better and better and better at over time as a pre-trained model for fine-tuning on new data sets. So here's the phenomenon I'm describing, where basically over many iterations of merging, which is what's shown on the x-axis here, we get basically better and better performance when fine-tuning on unseen data sets over this iterations of this like cold fusion procedure. And so the dashed gray line just shows the average performance on these held out tasks of the original pre-trained model. The green line shows what would happen if we took the pre-trained model and we did multitask fine-tuning on all of the data sets that are included in the distributed fine-tuning steps. And we can actually see that we outperform that by using cold fusion, by doing this kind of distributed iterative fine-tuning. So this, to me, really demonstrates the possibility of continually improving a pre-trained model by having end users fine-tune the model, communicate their changes back to the maintainers, and then giving the maintainers a way of incorporating those changes back into the original pre-trained model and make it better. So hopefully that convinces you that merging is possible and possibly possible and useful. So what's another thing that we need? Well, one of the really powerful things about open source software development, or just software development in general, is the modularity of software. So oftentimes if you want to add a new capability to your software, you can go get a package or a library that implements that functionality and bring it in and include it into your software. And this gives you a kind of modularity, okay? And the way that machine learning models are made and used now, there isn't the same kind of modularity. I can't basically say, oh, I want my model to work on this new task. I'm going to grab a set of parameters that I can just dump into my model, and now my model will be able to perform that task. There are model architectures that could make modularity possible. And here I'm highlighting one such model architecture called a mixture of experts model. The reason that these models would make modularity possible is because they route their activations through individual experts. And these experts are specialized typically to some particular kind of input, or maybe to a data set or a domain or a task. And crucially, the choice of what expert to use is generated by a learned router that adaptively decides how to route the activations in the model. Now, the choice of which expert to route the activations through is a discrete choice. And as I'm sure you know, we can't backpropagate derivatives through a discrete operation like the selection of expert operation. So in order to train models with a mixture of experts, people typically resort to gradient estimation techniques, like reinforcement learning style techniques that make it possible to approximate gradients through this discrete operation. And what we showed in recent work was that the gradient estimation techniques used to train models with specialized experts, specialized subnetworks, often failed to learn performance solutions. And so in really recent work, it's not actually even on arXiv yet, we showed an alternative way of building a modular model architecture that allows exact backpropagation of gradients, but still allows for specialized subnetworks, specialized experts. We call this method soft merging of experts with adaptive routing, or SMER. And what SMER does is, rather than using the router to select one expert to use, it uses the distribution produced by the router, the distribution over which expert to use, to merge the experts themselves, to average together their parameters. Okay, so we're going to take a weighted average of the experts' parameters, where the weighting is done in accordance with the router's predicted distribution over the individual experts. And in doing so, we end up with a single merged expert that we end up feeding our activations through. And as long as the expert choice is shared across the sequence, this has a cost that is basically the same as doing the conditional computation version, the discrete version that I mentioned on the previous slide. But crucially, because we can backpropagate gradients through SMER, what we find is that SMER actually outperforms every existing method used to train models with specialized experts. And it actually even outperforms what we call tag routing, which is a case where you can kind of hand design a good routing scheme. So for example, if you're training on a mixture of data sets, that come from different domains, if you route the examples through different experts in accordance with their domain, you can get pretty good performance. As you kind of think of it like an Oracle routing. And not only does the Oracle routing outperform all the gradient estimation techniques, which really suggests they aren't working that well, but smear actually significantly outperforms the tag routing, the heuristic routing. So, okay, so now we kind of have some of the ingredients for collaborative and continual development. We can communicate patches, we can merge things, we can kind of build model architectures that allow us to incorporate changes from other contributors very easily. Now let's talk about something a little more nuts and bolts, which is to actually build a system, a version control system for model parameters. So I need to be able to keep track of all of these changes that are going to be made to my model. I need to be able to automatically merge them and so on. And again, in work that is not 100% public yet, actually this Git repo is public, we've been building a version control system for model parameters that we call Git Theta. And Git Theta is a Git extension, so it sits on top of Git, and it allows you or the maintainers of a pre-trained model to keep track of updates to the parameters of that model. And so because it's built on top of Git, it integrates into your existing workflow. You can keep track of the model parameters right next to your code, but it keeps track of the actual updates to the model's parameters over time. Okay, and that includes it includes support for things like parameter efficient updates, like the stuff that I was mentioning much earlier in the talk. It supports automatic merging using the merging tools that we described. So if you create a pull request and someone else creates a pull request at the same time, and there's a merge conflict, now I can automatically merge those pull requests by basically doing smart parameter averaging. And so the code is public. We've kind of started to develop models using this workflow, and we'll hopefully have a paper out on the system by the end of the month. I have some slides that were supposed to be hidden on my notes, but I see that they're not hidden. There we go.
Should we? Should
yeah,
we go
sorry.
ahead
This is my last slide here. I'm happy to go to Q&A now. Yeah.
Sure. Well, yeah. This is a great. This was a really great talk. I know we all really enjoyed it. I know that we have a lot of technical questions in the YouTube chat, also in the Discord. But I wanted to kind of maybe start a little bit high level with a couple questions. I'll also go ahead and stop your screen share just so that the audience can see it. Okay, yeah, that's great. So I wanted to start with just a couple high level questions. So, as an academic myself, I find this vision of kind of collaborative, like building on these models really compelling, and all these techniques that you've been developing have been really awesome. I wonder if you can comment kind of maybe from an industry perspective, if you're somebody like Microsoft, you just released the new Bing, or your OpenAI. Can you maybe talk a little bit about what incentives they might have to open up their models and make it so that anybody can kind of contribute and work on models in kind of this big open way?
Yeah. So I think, there's one brief thing to say, which is that, industry still uses version control, even internally. And so a lot of the systems that we're building for collaborative development are applicable within industrial settings, but you're really asking about across the industry, public barrier. And, you absolutely, and again, I really like to rely on the analogy to open source software, but you do see examples of large companies contributing to open source software and releasing their models for collaborative development. I do frankly think it's a lot more complicated. It's a lot more complicated in open source software because of like contributor licensing agreements and all this stuff. But it would naturally be a lot more complicated in this case. And frankly, I think it would be great if large industrial groups got active in the development of these models, but I think that increasingly we need to not rely on them as much as possible. And part of the vision of this system is, or this research direction, is to make us less reliant on them to build pre-trained models for us. Because I think increasingly, as I mentioned earlier in the talk, large institutions are saying, we just trained this model, it cost $25 million. It's pretty valuable. Let's keep it to ourselves.
Right. kind of as a follow-up to that, my next question is, for people in the audience, or people in the class, or people watching the video, what are some of the best ways to kind of get involved in that open source community and start contributing to these projects? If they're really excited about this vision, really gung ho, how can somebody get involved?
Yeah, you're made me realize that I forgot to put a link on my last slide to we do have like it's not a Discord, it's like way less hip than a Discord. It's called a Zulip. It's kind of like it's actually an open piece of open source software that is better than Discord and Slack in every way. But we have a Zulip community for this research direction. It's bit.ly/cccml collaborative communal continual machine learning cccml-community. And if you poke around for long enough on my website or Twitter, you'll find it. But yeah, please join. And things are, we're kind of taking baby steps, but now the train has gotten some momentum, and I think that there'll be a lot of exciting projects that people can contribute to along this line over the next few months and years.
Great. I want to just get a couple technical questions from the YouTube chat, then I'll pass it on to Vonica and Michael to ask some questions from the class. So there's a couple of questions in the YouTube chat, kind of both around the same question. So one is, how do you deal with kind of model divergence? So is there somebody who will kind of decide how to train a model? Is there some committee somewhere? Do you do it via email like the old Linux days? And also kind of on the flip side of that coin, how would you detect kind of like a malicious model commit or something like that? Like maybe, some large corporation is trying to get into the open source and then decides to, has some way of making the model always point you to their website or something. Do you have any thoughts on kind of those questions like that?
Yeah, definitely. So I think, in the longer version of this talk, I have kind of a set of like what I think are the most important next steps for this research direction. And certainly a very important next step is just the broad excuse me, question of testing. Because, most of the time when we test a pre-trained model, we adapt it to some target tasks or domains, and then we see how well it works. And that kind of gives us the average case performance, and you could easily imagine if someone is contributing a change back to me, I could, test it just by adapting it to downstream tasks and seeing how well it works, making sure that the performance doesn't go down, and so on. But that's a very expensive and loose way to test models. And also it doesn't handle what I would call worst case behavior, which is kind of what you're talking about with malicious users. And so it's in the most general case where there's no way to kind of verify what data the model was trained on and how it was trained, tying into existing work on kind of like verifiability of machine learning model training, and also general like questions around robustness and detection of backdoor attacks and so on, I think will be valuable here. I mean, it is worth mentioning that open source software is unfortunately very vulnerable to malicious attacks. There have been, a lot of examples of, mostly hypothetical examples, but a lot of examples of vulnerabilities getting into open source software. And so I don't think that, it's not a problem that I think has an easy solution, but unfortunately there's been some groundwork along those lines too.
Great. Cool. So now I'll pass it off to Michael a little bit. I'll just turn my laptop around. We're actually all in the same. Okay. I think
this is a bit weird.
Yeah, it is. Yeah.
Sorry, we're all actually in the same room. Covers been blown.
Okay, I'll pin your video, and then I think the audio will still come out of me, but maybe this will work a bit better. All right, go ahead.
Yeah, so thanks, Colin, for the really great talk. Have a couple of sort of interesting questions from the class as well in the Discord. Sort of related to that notion of how do you protect against, let's say, malicious actors, but also perhaps like slightly less maliciously, right? I'm curious like what your take on is with respect to, let's say, viewing like this model merging sort of scenario as, okay, this is weird because there are like two cameras on me, but sort of like thinking about this with respect to like multitask learning, right? And a situation where perhaps let's say one sort of contributor wants the model to do well on one task, but another contributor wants the model to do well on like their task. How do you sort of navigate this? Do you sort of like the methods in, I don't know, Fish or the other techniques that you propose? Like, is there some way to sort of like handle, let's say, potential task interference?
Yeah. So I think you're highlighting one of the many ways that this general research program ties into existing work, because as you're pointing out, it's kind of unrealistic to expect a given model to work well on everything anyone could possibly want the model to work on. And in particular, as we know from multitask learning, continual learning, and so on, models have limited capacity, so they can't be good at everything. And so I think there's kind of apart from just continuing to work on improving, mitigating catastrophic forgetting and improving positive interference and so on. The other kind of strategy that we're taking in this research direction is to think about modifications to model architectures themselves to make it more possible. And the smear approach, having specialized experts, I think is a very promising way of doing that, because then, for example, if you have a backbone model that's just kind of pretty good in general, but then you have specialized experts that make it very good at individual things, it's very easy for you to have, a specialized expert for your task that you really care about, and for me to have a specialized expert for the one I care about without them interfering at all. So I think, if in the general case, these things are very hard and often well studied, but oftentimes I think we can make certain architectural design choices or assumptions that make some of these questions easier to answer.
Okay, thank you. Yeah, and so I guess, actually, let me see. Sorry, there's a couple, I'm just scrolling through the Discord. Sorry, I was caught up in your your explanation and like thinking about it, and lost my train of thought with respect to the questions I was gonna ask.
No problem.
Yeah, so maybe I'll just start with like, I guess you maybe touched on this a little bit, but yeah, people were also asking about like the sort of sequential nature of specifically like the techniques that you presented, such as Fish, right? So there's a question with respect to this, and sorry, 1 second. I guess, did you see that there was sort of like the ordering of sort of like the task merging matter? Or did you play around sort of like this sort of setting where, like, I don't know, and I guess it's a connection to, what's the word? Sorry, I'm blanking, but sort of, yeah, like merging from task A, then task B, did that perform better than, let's say, merging from task B to task A? Did the ordering matter?
Yeah, so order matters a lot less in at least the formulation of merging that we presented, just because we are doing like a parameter average. We didn't experiment too much with like really esoteric, like merging schemes where we have like many steps of sequential fine tuning on one branch and many steps on another branch, and when is it most effective to merge and so on. I will say that in the cold fusion results, where we do this kind of distributed fine tuning and averaging, it's really quite robust to basically like which data sets are included in each step. So I think there's a decent sense, especially in the fine tuning case where you're starting from a good pre-trained model, that some of these considerations don't actually make a big difference.
I see. Okay, cool. And I guess, so one question related actually to the cold fusion. So you had that graph, which I found pretty interesting, that the sort of decentralized, I guess, multitask, is that was on the plot?
Yeah.
Perform better than just the multitask. And do you have an intuition of like why decentralized help?
Yeah, so there's we have some other kind of preliminary work that may go on archive soon about that too. But there is kind of this, and I can't really provide a lot of justification here, just more of like observations, but it does seem to be the gradient descent is not very good at finding like a good generalizable solution. Basically, and this shows up and basically that like parameter averaging is better in some cases, and this shows up in a lot of cases. Like if we go, I don't have my slides show now, but actually one thing that astute observers might have seen in the robust fine-tuning result is that by averaging the fine-tuned parameters back with the pre-trained parameters, you can actually get better performance on the fine-tuned task, which is kind of crazy, right? That means that gradient descent, the fine-tuning process, went to a region parameter space that was worse than if it just stopped partway. right? I mean, of course, it's not a linear path between the two, but this is kind of odd, right? And the same thing is true, it turns out, kind of in the multitask setting. If I take a pre-trained model and I do like individual multitask training and average the results, average the corresponding models together, that can often be a better starting point as a pre-trained model than doing multitask training. So, I think we often think of gradient descent as like finding the best possible solution, but I think the ability to do this like parameter averaging and interpolating has started to uncover the fact that sometimes there are good solutions that are nearby that gradient descent has failed to find.
Right. Yeah, that is interesting. And I think it actually also, so last week we had Ludwig on, and it touches on some of like the work from his group as well, of like the model soups and the sort of like subspace averaging, where it's pretty interesting that you can discover, let's say, like these like I don't know, manifolds or spaces in like, let's say, neural net parameter space where you might imagine that there are certain parameterizations or things where the averaging just works better and you can just try to find them, but regular training on a single task might not get you there.
Yeah. Yeah, I think it's not well understood yet, but it's a really interesting observation.
Cool. Thanks. Yeah, maybe I can just try to find one more question. But if not,
I can take back over.
Thanks,
Michael, for asking those questions, and thanks to everybody in the class for watching. Your questions are always really great. Colin, right as we wrap up, I just wanted to give you a minute to talk about kind of what's next, what's really exciting for you coming up. What can we kind of like expect in this space going forward, and what are some things that you're kind of just really excited to continue to share and work on?
Yeah, definitely. The really short-term stuff that I'm excited about is actually building models in this way, which we're hopefully going to do over the next like 6 months, let's say. I talked about smear. Hopefully we're going to start building a model in that way where people are adding and updating individual experts and so on, getting a better and better and better multitask model that just works on more and more and more tasks. We're also going to hopefully do like a very large scale cold fusion run where we're just taking the pre-trained model, everyone's fine-tuning it and passing their updates back, versioning it via Git Theta, doing automatic merges, better and better pre-trained model, and so on. That's a very short-term exciting stuff to me. The long-term exciting stuff to me kind of revolves around the fact that I actually think that this analogy that I've made about machine learning models and open source software will start to fall apart. And the reason it'll fall apart is because most of the time when people use, like an end user of a machine learning model usually has data that they want to feed into the model. And a lot of the time they know what the model should output. And that's not true in open source software, right? Because in a given piece of software, it's actually relatively rare that a downstream user wants to change what the piece of open source software does. I mean, how many of us on this call have contributed patches to Python? I mean, it'd be great if some of us had, but I doubt it. But again, with machine learning models, we often do want to, and it's much easier to change the model. So I think it'll be much more likely that rather than having kind of like a single source of truth, we'll have this big ecosystem of variants of a model. And it'll be, thinking about how to decide which of those models I should use and combine and merge together to make my starting point for the task that I care about. And then I'll pass that back. I think we'll create like a really, really rich ecosystem with a lot of interesting problems.
Great. Yeah, I totally agree with you on that. I think that's completely spot on. And really looking forward to the day when we get to, all have our literal own custom model that does what we want. So with that, I think we'll call it for today's seminar and today's class. Thank you to everybody in the audience for participating, asking questions. It's one of my favorite parts about doing this. Next week, we have another two-parter. So we're going to have Raphael Townshend on Monday talking from Atomic AI about some medical applications. And then on Wednesday, we're going to have Rob Reich. And I'm sure he'll have lots to say about kind of model provenance and the ethics of all this stuff that we're doing. So if you're listening and you want to tune into those, you can go check out our schedule on our website, mlsys.stanford.edu. We have a mailing list where we send like 2 emails a week. So no spam at all. And of course, subscribe to the YouTube channel, hit that bell icon, do all the things that you do on YouTube to get to figure out when things are happening. And with that, I think we'll say goodbye to everyone. So thank you all for watching, and thanks again so much, Colin, for giving a talk today. It was a lot of fun.
Great. Thanks for